Hi everyone, I'm Shang Zhou from University of Nottingham. Today I'm happy to talk about our recent work using a novel semi-analytic spectral fitting approach to analyze the evolution of a sample of manga spiral galaxies. This work is collaborated with Mike and Alfonso. If you are interested in this work, you can just come to me. Our work is under a big context of galaxy evolution, and we all know that galaxy forms in the center of the dark matter halo. The formation and evolution of the dark matter halo and the large-scale structure it inhabited, it's already been well understood because we now have very high-resolution cosmological simulation, and also because the physics behind this evolution is only gravity. It's very simple. But when we consider the galaxy form in the center of the dark matter halo, if you have a large wealth of complex baronic physics, which means the evolution of galaxy become very complicated. So the evolution is still remain unclear and is a very hot topic in astrophysical studies. To understand the evolution of a galaxy, we always need observations. In the past 20 years, people have collected huge amount of spectrum from the galaxy. In the era of Sloan, we have the single fiber spectroscopy that can point at the center of the galaxy and get a spectrum like this. And with the advent of integral field spectroscopy and those large surveys like MANGA, we have the integral field spectrum of like 10,000 galaxies in the MANGA survey. For each galaxy, we have thousands of spectrum for it, and these large amount of spectrum significantly improve our understanding of the galaxy evolution. So to obtain the physical properties from the spectrum, we need a good tool to fit the spectrum, and this is the so-called spectral fitting techniques. And traditionally, we already have several spectral fitting approaches. For example, the Starlight, PPSF, or Firefly. Those are the so-called SFT-based methods. You can just decompose your observed spectrum into linear combinations of XSP-based SV templates, and then you get all the weights of the templates, and you get the star formation history and the chemical evolution of the spectrum of the galaxy. But the problem is, as we all know, that we have significant degeneracy between age and metallicity, also for other parameters. So are these fit models physically possible? And what's the physics behind these stellar populations derived? These questions motivate our method. We intend to go beyond the stellar population itself and to understand the physics behind this stellar populations. So we consider several physical processes that govern the star formation activity in the galaxy. We have considered the inflow and outflow of gas and star forms and the star gas cycling inside the galaxy, how the stars form in the gas cloud, and they enrich the metals, and when they explode, they will release the metal-enriched gas into the interstellar media. Combining all those physical processes together, we are able to construct a chemical evolution model and predict the evolution of the galaxy, the star formation history, and also the chemical evolution history like this. Our work incorporated the chemical evolution model into the spectral fitting procedure. We are using parameters to given a set of model parameters into the chemical evolution model, we can predict the star formation history and chemical evolution history, and we convert this information with SSP templates. We can calculate a model spectrum. For comparing this spectrum with the observed data, also we collect additional information from the gas phase, for example, the current gas phase metallicity and also the star formation rate. We combine all those information together to calculate a likelihood and return to our sampler multi-nest. And when the sampler run this loop again, they sample all the parameter space, you can get the posterior distribution of your model parameters and the evidence. This is an example showing the results of applying our model to a manga galaxy. Here we stack the spectrum within one effective radius and fit with this method. We got the star formation history of the galaxy and also the chemical evolution history. Then we apply this method to a sample of spiral galaxies selected from the manga survey. This is the result we got from the plot on the left. We see the star formation history of different mass of galaxies of different stellar mass bins. We find that those massive galaxies accumulate their stellar mass earlier than low mass galaxies, and this is the so-called downsizing formation. We produce this downsizing formation naturally from our fitting. So this downsizing formation is physically allowed by our chemical evolution model. Also, we derive the chemical evolution history from our model as shown from the left panel. We see that massive galaxies not only accumulate their stellar mass earlier, they also be enriched in their metallicity earlier than these low mass galaxies. And you can see from the cumulative plot on the right hand side, you find that these low mass galaxies has high fraction of low metallicity stars. In contrast, those high mass galaxies has only low fraction of low metallicity stars. This problem is already known as the G-dwarf problem in our Milky Way, because if you think the galaxy evolved like a closed box, you will expect the cumulative distribution like this. Our result naturally tells you that a Milky Way-like galaxy cannot be a closed box. In addition to the star formation history and chemical evolution history, we intend to look deeper into the physics. Here we are showing the results of the gas mass evolution of the galaxy. On the left, we are comparing our predicted gas mass fraction with those observed by H1 manga survey. You can see that we successfully reproduce the mass dependence of this gas ratio. We see that low mass galaxy have higher fraction of cold gas, while high mass galaxy has lower fraction. And we can trace these back to the early universe and to figure out whether those difference can already be seen in the early on or just happen in recent times. We found that the mass dependence of the mass ratios is more apparent in the recent 4 gigayears, and it's when we go further beyond like 8 gigayears ago, all galaxies tend to have similar fraction of gas. And in addition to the gas mass, we can go even further. In our model, the gas amount in the galaxy is governed by the inflow and outflow of the gas. So in this plot, we are showing, on the left plot, I'm showing the gas inflow timescale versus stellar mass of the galaxy. You can find that low mass galaxies have a longer info timescale of gas, which allows it to have more extended star formation history. And from the plot on the right, we are comparing the outflow strengths for different mass of the galaxy. You also see that low mass galaxies have stronger outflows, and least strong outflows suppress their metallicity enrichment process in the early universe. So you see the downsizing of the chemical evolution. In addition to look at the all galaxy as a whole, we keen to look at the dependence of the galaxy evolution on the environment in the habitat. So in this work, it analyzed samples of galaxies from isolated central and satellite galaxies to trying to investigate the environment effect in those galaxies. And these are the results we got. In the first row, we are showing the cumulative star formation history of different categories. Look at these massive galaxies. You can find that these low mass satellites tend to quench their star formation early on, while those central galaxies will have quite strong star formation recently. This has already been observed by the higher fraction of satellite galaxies. Higher fraction of red galaxies in satellite galaxies than in central galaxies. And if you look at the chemical evolution in the bottom row, you can also find that the evolution is quite different. Satellite galaxies evolve like a closed box or leaky box, which means that they don't have enough gas supply to the galaxy, while central galaxies evolve more like a creating box, showing the continuous gas supply to those central galaxies. And this difference in the inflow and outflow properties can be directly observed from our best fit models as shown in these two rows. The first row we are showing the gas inflow timescale, and you see that low mass satellite galaxies have like shorter inflow timescales, so that they quench early on. Also, you can look at the outflow strengths. You see that satellite galaxies have stronger outflow strengths. These very strong outflow can suddenly remove the gas reservoir in those low mass galaxies and quench their star formation. Those are hints that those low mass satellite galaxies might have experienced speculation due to interaction with other group members. They cannot hold their gas reservoir, and the gas is removed and quenched. This is a direct evidence indicates that though the environment has played an important role in shaping the evolution of those low mass galaxies. And this is all of my talk. I'm introduced to you our novel semi-analytical spectral fitting approach, and we have applied this approach to sample of manga spiral galaxies to recover the downsizing information and the physics behind the downsizing, and we also look at the environment dependence of this evolution. And thanks very much for your attention.